Hello. Thanks everyone for coming. Very nice to see the room full. Almost full, right? Anyway, so how do I move to the next? Oh, here, mouse. Right. Oh, this thing. Okay. All right. Okay. So some of the things that are going to appear in the slides have already been presented briefly. So first thing to know that perhaps summarizes a great amount of the things that I'm going to be talking about is that inference in the cortical surface, as far as a p-value is concerned, is not particularly different than what we do in voxel-based analysis, that is using volume-based representations. The prototypical method that we use, can you hear if I stay away from the microphone like this? No, I have to be like this. Okay, all right, fine. So we use it, the simplest way, the most prototypical way is using the general linear model. In the general linear model, what we do is we start with measurements that we obtain for every participant that we have, and we model those responses that we have obtained using a matrix that contains the effects we are interested on. So our data is going to be in that vector y. Our design matrix that's going to contain our variables of interest are going to be on the x. We don't know the betas. The betas are what we are going to try to find. And we try to find that by minimizing a certain residual term that is our error vector there. So making this more concrete with numbers, we could have something like this. Let's say you have 25 subjects. In each of them, in a given voxel, you measured a bunch of, let me go back here. In each of them, you measured a couple of values. This could be, let's say, cortical thickness, it could be cortical surface area, it could be fMRI bold signal, it could be anything. And then let's say you want in those 25 subjects, see how, let's say, a cognitive measure, let's say in this example, the MoCA, helps to explain those values that you have observed. And let's say that you also want to take into consideration that many of your subjects may have different ages. Some are men, some are women. So you include those terms, those nuisance variables in your design, and you also include an intercept term because we have to, right? It's the same as mean center in the data. And you don't know what's the relative contribution of each of those variables. So you want to calculate this. And you want to calculate this in such a way that you minimize this vector of residuals. So, well, here the numerical examples are already included. So these are the actual values obtained after estimating. And like I said, you are interested in one of those values. So by using a contrast that Laila mentioned earlier, we can isolate just that effect that we're interested on and plug in into a formula. Now, this is a very basic formula. This is just for the t-test, but of course we can do much more sophisticated analysis. But in the case of the t-test, what we do is we estimate our beta that we're interested on, let's say the beta for the MoCA, and we divide that by the standard error of that, which is a quantity that depends on the residuals that we tried to minimize earlier. And once you have the t, then that's relatively easy to obtain a p-value. And the way as we do that is, well, in two ways. Either we use what we call a parametric test, so we essentially just look into, thanks for closing the door, whomever did that, thank you. We do that by looking into the distribution of the test statistic and by imposing some assumptions, or we do a permutation test. And by permutation test, I mean, we go back to our design here, and we permute something in this design. Now, this design is fairly complicated, because it has also nuisance, so we can't just permute everything. There are different ways in which you can permute, but in the simplest form, we could just permute this vector here. We keep everything else unchanged. We keep this unchanged, we keep this unchanged, and then we permute just this. Permute once, recalculate that t-statistic. Then do that again and again and again and again, and keep doing this until you find the distribution of the test statistics that you would have observed if there were no effect of the MoCA on your results. And then that leads you to obtain a p-value. Now, you got your p-value. Now, what do we do with it? Well, we have two things at this stage. We have the t-statistic, the test statistic, right? And I mentioned the t as an example, but the same works for f-statistic, or even for things that are not based on that kind of inference. It could be, let's say, coefficients of ICA, of PCA, of some other fancier method that you may have. What we do with that? Well, the signal may be spread across the surface, right, or the volumes if you use a volume-based representation. So you can apply a threshold and see what's the size, see how many blobs survive and how big those blobs are. And if you calculate the size of the blob, that gives you a quantity, a cluster size. You can also do something else. You can also calculate the sum of the test statistics that are within that blob. That gives you another statistic that we call cluster mass. Cluster extent, cluster mass depends on a threshold that you apply to the image. And that threshold is somewhat arbitrary, and people don't like that kind of arbitrariness very much. So a way to bypass this arbitrariness is by replacing that single threshold by a number of thresholds. And based on that idea, you can use something that is called TFC, threshold-free cluster enhancement. So the idea is that you get your statistical map, right, the image that has all your t-statistics, and apply not one, but about 100 thresholds. That's what is used in practice. The formula, in fact, is an integral, but we never use this integral in practice. We always make it discrete, so this becomes a sum. And you apply this 100 thresholds, and then for each level, you solve this formula, so you get the extent for that threshold, and multiply by the height that you're using, and you raise these to some numbers, and you sum of these together for all of them, and then, boom, you have your TF statistic. And that number, you get one for every voxel. So again, once you have that, you can calculate the p-value. Now, unlike the so-called parametric tests, in which you can use just a formula to obtain the p-value, here you have to resort to permutations. It's necessary. There is no alternative. All right. So in the case of the parametric test, you have a formula that tells you how the statistics are distributed. This formula is based on a number of assumptions, and your statistics have to be properly calculated, and you have to know how the data are formed, what's the data generating mechanism, and the good that it's very fast. But if the assumptions are not correct, then this nice formula that gives you this nice curve doesn't apply anymore, and then the results are not accurate anymore. Now, if you use a permutation test, then you don't depend on that anymore. Now, your distribution can be somewhat crazy like this. It has no assumptions or very minimal. The only assumption really is that the data are exchangeable. By exchangeable, I mean that when you permute the data under the null hypothesis, the data that you find after permuting is just as likely as the original data that you have collected. And if this holds, and that's really the only assumption, there is nothing further, then the test is valid. So it requires no prior knowledge on the data, unlike this case. But the downside is that it's computationally very intensive. Whereas this one, even for a whole image, you can obtain in a fraction of a second. This one may take hours to compute. I would say it still pays off because we spend thousands of dollars, sometimes millions of dollars collecting data, right? So you're not going to be put away just by a couple more hours running that. But anyway, sometimes it can become an issue. All right, so you got a p-value, one p-value for every point in the brain, every point in your image representation of the brain, which can be volumetric, can be surface-based, or any of the other ones that Janine mentioned earlier. And now you have, for every p-value, for every point you have p-value. Now, by virtue of how p-values are defined, even if the null hypothesis is true everywhere, you are still going to find many false positives. If you use a p-value, a test level of 0.05, let's say 0.05, 5% of all your results are going to be false positives. And that's a no-no. Nobody wants to have that. So you have to correct for multiple testing. There are many ways in which you can correct, but all of them fall into two categories. Either you correct what's called family-wise error rate, in which you control the chance of committing even just one error across your whole image, versus false discovery rate, in which you control some other quantity, which is the fraction or the proportion of false discoveries that you're going to have in the image. So in the family Y08 example, if you correct using that, if you keep repeating the same experiment 20 times and you use 5% as your test level, in only 1 out of 20 you see any error anywhere in the image. If you use this other method that is also does family Y08, the so-called random field theory, I'll comment more next, the same happens. Now the results are still different because the theory of this and the so-called bufferonic correction, they're based on different assumptions and certain things you have to do with the image to be able to apply each of them. False discovery rate, on the other hand, for every realization of your experiment, you are going to see false positives in many places in the image, but the amount of those false positives is controlled. In this case, 5%. This is another example. So let's say you correct instead of 5%, you use 10%. If you don't apply any correction, you're going to find about 10% errors everywhere in the image. If you use FWER, so family-wise error rate, in 1 out of 10 experiments, you find any error somewhere. Now, this slide here, the resolution is small, we cannot see, but actually there is one false positive here. We cannot see in the screen. I cannot see. I'm very close, I cannot see myself, but in the slides, it's possible. So if you download the slides later you'll be able to see. By the way, this figure is very famous. It has appeared in many places. You find, it was Tom Nichols who created this. You find, for example, in Jeanette Montfort book, which is well known. So this figure is well known. You don't need this slide to see this one in particular. But the fact is that there is a false positive here. And if you control the false discovery rate at 10%, then 10% of every discover of every set of discoveries, so every repetition of the experiment will contain that amount of errors. So the random field theory, this was used a lot in the beginning, let's say throughout the 90s and early 2000s. It was very much used, and the idea of the random field theory is this: you want to correct for the amount of errors. All right, fine. So what does this mean? Well, it means that if your statistical map, if you model this as a random field, which is essentially a random, it's a map of random values that have some spatial information in them. If you have some properties of this random field, you can find out what's the probability of finding the maximum value of this field above a certain threshold. And if you know that, the likelihood of that happening, then you can reverse the formula. So what would be the threshold that I could apply to have the number of surviving blobs there being equal to the error rate that you want to have? So let's say 5%. And if you do that, you calculate the threshold, and that corrects that for you. So the main problem with this is that it's based on many assumptions, and many of those assumptions are very unrealistic. For example, the residuals of the GLM, they have to be normally distributed. The statistical maps, they have to be a good, whatever that means, representation of an idealized, continuously differentiable, by the way, I didn't write here, but it has to be that too, continuous underlying random field. And we have, because this never happens in reality, not with MRI-based imaging, we normally have to apply smoothing the data. So smoothing becomes a requirement of the methods, and people normally don't like that. Also, the degree of smoothness, it has to be constant throughout the image, or you have to know the degree of smoothness in every point of the image. And that's also very unrealistic. And by the way, you have to smooth that. We have to estimate the smoothness. And every time we estimate something, we are prone to errors. And also, you have to assume this, that suprathreshold voxels, so after you apply the threshold, right, they must not touch the border of the random field. And that's also fairly unrealistic. And because it's so complicated, also, it turns out that the full implementation, as the random field theory is supposed to be, it's available in very few software packages. SPM has it, but not for surfaces. FSL has it, but it's a simplification. Affinity has it, but it's also simplification. So it's not very much used anymore. So the idea is that, so this is a random field, right? Slice through it. Let's say this could be an image, and it looks fairly random, right? And this is the same, right? It's just two representations of the same thing. And if you apply a threshold sufficiently high, let's say in this case it's about 3, then you have some blobs surviving there. And the random field theory, it tells you how many blobs you have as long as all those assumptions are satisfied. And if you equal the number of blobs to 0.05, which is the test level that normally we use, then we figure out what's the threshold that you have to apply. So what's the height that you have to cut this map. And the formulas that you need for this, they are like this. Now, the reason why we don't like the random field theory is not because the formulas are complicated. In the end, we can deal with all this. So we just write software that's going to deal with all the situation. The main problem is that some of those formulas require terms that are difficult to calculate. They require spatial derivatives, and they become very sensitive to noise. And we need that to be able to estimate the smoothness of the data. And the smoothness of the spatial map is one of the parameters that we need to make those calculations. So it's very easy to get this wrong. So we don't like to use that very much, but it's still available in some software, and be aware that this exists. You may stumble on this, and you may eventually want to implement yourself for your data. And by the way, if the assumptions are valid, all those assumptions are valid, the results are actually accurate, but the assumptions must be met, and you have to be able to make all those estimations yourself correctly. All right, so if we don't use false discovery rate, if we don't use the random field theory for family-wise error rate, what can we do instead? Well, one, we can use false discovery rate, like I said earlier. There are a number of methods. Some of you are familiar with this. I assume it's a well-known approach. Normally, when you speak about false discovery rate, we are talking about this procedure developed by Benjamini and Hochberg. It controls the proportion of false discoveries, but this is something that not many people is aware of. What FDR controls, this procedure controls, is not really the exact FDR. It gives you an amount of error rate that depends on the number of tests in which the null hypothesis is true in relation to the number of tests that you have. So let's say you have V voxels or vertices or whatever, and you have a number V0 of tests in which the null hypothesis is truly true, in which really there is no effect whatsoever. FDR controls not, FDR controls not the value that you want, which we normally put in this variable Q. It controls Q times this fraction. So if you have lots of tests in which the null hypothesis is false, that is, you have lots of signal, you actually can get less errors than you want. And they may say, oh, that's great, so I get less errors. Well, not really, because if you're looking at a map, you think you have, let's say, 5% errors there, but you have less, then you are being wasteful. You are throwing away information. You could be using more of data than what you actually have. So Benjamini and his collaborators, a few years later, they proposed a slightly improved version of that. So whereas in FDR, we use this formula. It's very simple. I will describe this in the next slide. You use this other formula. It just looks a little bit more complicated. But the solution, if you use this in this BKY procedure, then you actually get the precise, the sharp amount of false discovery rates that you want. Unfortunately, the BKY is not available in any imaging software. But we are going to remedy that very soon. So keep your eyes open, and very soon there will be software that's going to do this. All right, so how these procedures work. For the BH procedure, what you do is you sort your p-values in ascending order, and then you apply a threshold line that is inclined. The slope of this line is determined by the Q that you want. So you determine that slope. More false discoveries you want, you make that slope higher. You make it more steep. If you want less false discoveries, you make it more horizontal. The BKY procedure, the idea is the same. It's expressed by that formula, but the idea is that for every p-value that is sorted here, you actually vary your threshold a little bit further. So for the first one, the threshold is very similar to this. Not identical, really, but it's very similar. The difference is negligible. And from the second onwards, the threshold is always higher. So you become more and more liberal as more p-values become significant. And that's how the procedure works. And it gives you more powerful. It gives you more power. The procedure is more powerful. All right, and what about permutation? Well, I somewhat already described, so it's based on this assumption of exchangeability. You build the distribution based on the data itself. You have the test statistic that was obtained without any permutation. You count how many are higher than that, divide by the total number of permutations that you did, and that's your p-value. So super simple. even although it's slow. We already saw this one, so let's skip. Now, Janine already spoke about different representations of the brain, so we don't have to cover this. And also, Matt already described the idea of safety. But this slide is helpful anyway because it shows that you are not constrained about using just one representation when you are doing your analysis. You can actually mix them. And there are many ways in which you can do this. One is by using the safety format, that is a hybrid that includes a volumetric representation for subcortical structures, including the cerebellum. It's very hard to get surface-based representation for the cerebellum, from MRI at least, in the resolutions that we use. And you have a surface-based representation for the cortex. And you can use this in a hybrid manner in your analysis. If you use HCP-based pipelines, that is a given already to you, which is good. But even if you are not using that, there are ways in which you can do combined inferences across different representations. I'm going to comment on this shortly. All right, I added these slides just now, so I hope I'm not going to run out of time for these extra slides. So, if you use a surface-based representation of the brain, it's relatively easy to calculate area and thickness, as Laila commented earlier. But for volume, we can obtain that, the volume of the cortex, right? We can obtain that as approximately being the product of area by thickness. Like Laila said earlier, it's an approximation. But we can actually get those results exactly. So if we multiply, and let's say you calculate the area here in the white surface, and you have the thickness. If you calculate the product, we are actually calculating, imagine this were 2D, right? This is a schematic. So if this were in 2D, we would be calculating the areas of those rectangles here. But then in the gyri, we end up not counting some volume that actually exists there. So you underestimate volumes in the gyri. Whereas for sulci, we end up over-representing. There are some piece of volume that we end up counting multiple times. Now in 3D, this becomes just a little bit more complicated because now, well, it's three-dimensional. So those rectangles, they become these little prisms, irregular prism or prism, however you pronounce in English, I don't even know, but you get the word, right? And they are irregular. But we can calculate analytically their volumes because we have the coordinates. So what we can do is split each of them into 3 tetrahedra, irregular, and we have the coordinates. So we can calculate the volumes of each one of them. And when we add together, then we get the volume of that area. So we can do that as well. That gives a more accurate. So we're not always constrained to using volume by area. And if people criticize gray matter volume as being the product of thickness by area, that criticism, how can I say, it's not a valid criticism because we can actually calculate that in a very precise manner. There are other issues with volume though. It's genetically a mixture of thickness and area, and we don't like to mix those things, but that's a separate story. Like I said, if we have volume and volumetric representation of the brain and surface-based representation of the brain, we can still do joint analysis. And if there is a mapping between them, we can embed that in our statistical procedure. And one way of doing that is with permutation tests. So this is one of the slides that I just added, and again, I hope I don't run out of time because of this. So let's say you are interested in measuring, you think you have some kind of disorder that simultaneously alters cortical thickness and myelination. Suppose you have that. Well, you can do an analysis of cortical thickness, and that's going to give one result, and then you can do an analysis of myelination. That's going to give you another result. But I have 2 results, and what do you do with them? And plus, if the signal is weak in each of those 2 modalities, you may not be able to detect in either of them. So we have 2 results that are not very powerful. How about if there were a way in which you could combine those 2 types of data together and do a joint inference that could not only give you just one answer, but even better, could give you more power, more statistical power, more sensitivity to detect eventual results? Well, that method, it turns out, it exists. It's called non-parametric combination, or NPC. So the idea of NPC, well, first of all, it only works with permutation tests. And the idea is this. you have your different modalities. You do the permutations in synchrony across them. So this means that your design matrix of the GLM, remember the first slides, the design matrix has to be the same. So you can do the permutations synchronously across, which means they don't have to be the same time. They can be offline. Let's say first you do for one, then you do for the other. But the indices of the permutations have to be the same. And then for every one of those permutations, you calculate the test statistic, you build sorry, not for every one of the permutations, for every one of the modalities. You do the permutations in sync, and then you build the empirical distribution. Now, of course, because they are different modalities, the null distribution may be different for each of them. And then for each of them, you're going to get the p-value. But don't just calculate the p-value for the unpermuted data. Compute the p-value for every one of your permutations, which essentially means compute the cumulative distribution function, right, the CDF. And if you have that, then you can combine the results for each one of those. And because you save those permutations, you automatically, without any extra step, you already have the test statistic for the combined data. And then that allows you to combine, to obtain a result that refers to all those tests simultaneously. Now, the way as I just described, it turns out it doesn't work with imaging for a number of reasons, but there is a modification to that, which is described here and in the paper. In the end, the idea is essentially the same, but we do some modifications to accommodate some things that we cannot do with imaging data. Imaging data is too big, and if you do just like as I described, the p-values are discrete, and when you combine, then we actually lose power. But if we use this or the modified algorithm, which I'm not going to describe in full here, but the figure is here, it has a few extra steps that we add into it, then this becomes possible. And then you are able to do this joint inference that gives just one result. All right. Now, what I have said so far applies more or less identically, regardless whether your data is volume-based or surface-based. But there are things that actually differ, and you have to be aware of those differences. Otherwise, it could have consequences for some of the analysis if you do later, particularly if you use, let's say, hybrid formats, such as those of the HCP pipelines. So, first of all, for some statistics, like cluster extent, cluster mass, we depend on the spatial contiguity of the image elements of the representation that you are using. So, if it's voxels, you need to know how voxels are neighbors one of another. And if it's surfaces, you need to see how vertices are connected one with another. And the idea is more or less like this. So for voxels, you can look right what the neighbors are. And this is relatively easy to do because the voxels are always follow a regular pattern. So you know where a voxel is, you always know who the neighbors are. For surfaces, even after we have done resampling to the FS average, the surfaces is not perfectly regular. Now, here's a bit exaggerated, it's very irregular. This would be more a subject level surface. But even after we put in FS average, still there are irregularities there. The triangles in this common space is not the same. Not all triangles are of identical size, and the edges are not, they don't have the exact same length. So there are some irregularities there. And there are some singularity points as well, in which the number of neighbors is not the same. So we have to visit all the neighbors, and this adds some complications. But there is a way to generalize all those things simultaneously, and that is by computing an adjacency matrix across all the elements. And this works for both voxel and surface. Now, this makes the algorithm a little bit slower. If you look, if you assemble, let's say you have 100,000 vertices here and 100,000 vertices here. So this matrix becomes very big and it becomes slow. But if we have this, then we are able to calculate clusters that don't have to be connected one of another in space. Remember one of the earlier slides that I commented about cluster extent and cluster mass? So this uses clusters, this requires the clusters to be formed by voxels that are connected one with another, or vertices that are also immediate neighbors one of another. But if we use this generalization that works for vertices or for surfaces, and is based on the adjacency matrix, actually we don't need that anymore. Actually we can have clusters that are disjoint one from another. And why is that interesting? Why does this matter? Well, let's say you have an effect you think may be present in your data, let's say some connectivity effects, but you want to see if the result has to do with some actual measure of connectivity that you may have obtained, let's say using functional connectivity or tractography. So you can derive your connectivity, your adjacency matrix, based on, let's say, how different parts of the brain are connected based on tracts. And then you can use that to inform how your clusters are formed. And that gives you another way of establishing cluster level inference that works with surfaces, voxels, or anything you may have. This is in a recent network neuroscience paper, by the way. It's going to appear soon. All right. So hybrid representations like that of the CFT format, right, use the surface and voxel combined. They give you improved localization, right, for the reasons that have already been explained, better alignment of homologous regions. But where it comes to spatial statistics, recall that for clusters, we are using different types of neighborhoods versus surfaces. So let's say you want to, let's say you did an analysis using the CFT format, and therefore you have cortex and subcortical structures. Now you still need to correct for multiple testing. The methods that I commented, like random field theory, FDR, and so forth, well, not FDR, but the other methods, they require, and the ones that use spatial statistics, the ones based on cluster extent, mass, and TFC, they require this neighborhood information. In the case of surfaces, that neighborhood is established in 2D. In the volume, it's based on 3D. When time comes for you to do multiple testing correction and mixing those representations, it turns out that they are not perfectly comparable because if you calculate clusters in volumes, well, it's a volume, it's not the same as a surface. The units of measure are going to be different. They are not comparable. And it turns out, and it really happens, the distribution of one of those dominates over the others, and the test becomes very conservative for one of those modalities. So the way that exists today to accommodate this is by using that's the only solution, I'm afraid, is using Monferroni or this other method called CDAC, which is very similar, but just a little bit more powerful than Monferroni. The idea is this. You still use the other methods. Let's say use random field theory or permutation test to correct for multiple testing, considering each of those representations separately. But when you combine them, then you use one of those methods. So let's say you have two hemispheres, left and right, and you have the subcortical structures. You correct them using, let's say, Monferroni over 3 in this case, right? You only have 3. So you still do the family-wise error rate correction of each of those 3 parts, left and right hemispheres and the subcortical volumes, but you do a Monferroni over considering that you have 3. And like I say, that's the only way as of today. All right, let's talk a little bit about parcellations, super quick. This has already been presented, so no need to revisit. Parcellations are great if the signal that you would like to find matches perfectly or fully occupy an entire parcel. If the signal that you are interested on is smaller than the size of the parcel, then that effect becomes diluted, and then you lose power. Likewise, the effect may be split across different parcels and not fully occupying that parcel. And when that happens, then you also lose power. So let's look at this diagram here that has some toy examples. So let's say you have some area of activity here, and you have a nice parcellation that turns out your area of activity occupies essentially all of it, or all of 2 parcels. Then that's great. You have the very best SNR you could possibly get. This is the most powerful situation. But if you have, let's say, a tiny region here that is at the convergence of 3 different parcels, then that small area, that effect is going to be spread across those 3 parcels and gets diluted, and you may not be able to detect anything. Now, in those cases, then not doing the parcellation and doing the analysis vertex-wise is going to give you more power. Well, but then not really, because the advantage of using the parcels here is that you average the signal within parcel. That's where you get the boost that's going to give you power. And then if you use a resolution that is too high, the signal in relation to the noise is not going to be maximized in any way. You may still fail to detect. So there is a sweet spot, more or less, between the resolution that you are going to be using, and by resolution I mean not only the size of the voxels or the size of the parcels, versus the actual power that you have in your experiments that is based on the number of subjects that you have or number of time points that you have for fMRI. And that depends on the modality, unfortunately. But it's a trade-off that needs to be considered. And if you use if you don't use parcellations, if you use vertex-wise data, you be aware of this. Perhaps not everybody knows that you don't have to limit yourself to the resolution that is given to you by the pipeline that you are using. You are always able to sample the resolution further down. Now, of course, you don't want to come here, right? Because then you are really losing resolution. But let's take free surfer, for example. Like Lala commented earlier, we have about 110,000 vertices per hemisphere in native geometry. And when we put that into FS average, that's 160,000 vertices. So the brain is highly, highly upsampled there. We have subvoxel resolution. So in fact, we can afford downsampling a little bit and trying to improve to some extent our SNR, even if for some reason we think the areas that we are looking to find effects are not going to match our parcellation scheme. So you can reduce, let's say, to here or here. And you can see this as a form of data reduction. And you may have to do that anyway. For example, if you have, let's say you want to do functional connectivity and you don't have enough time points, you may benefit from doing connectivity by using a lower resolution if the parcels are not what you want to do. But I want to highlight a point that Matt made earlier, that if your parcels match very nicely areas that certain physiological areas, then it's to your advantage to use those. Anyway, I have commented this already. A substantial amount of the things that I commented here are available in Palm, which is a tool for doing statistical inference. The only thing that is not available yet in Palm or not in any software is the BKY method, but that's going to be remedied soon. And that's essentially it. So in short, recommendations. Use permutation tests whenever you can. It's better. Surface is better for cortex. And in terms of resolution, parcellations are superior whenever they match the extent of the signal and may be necessary as well as a form of data reduction. And that's all I had to say. Please reach out to me if there is any question. I'm happy to discuss any of those things. All right. Thanks, and sorry for extending a little bit over time. 2 minutes to be precise. Thank you. All right.